Assalamu alaikum. Our project today is image caption generation. We're using the Flickr 8K dataset. We are using it because it has 8,000 images as well as captions. Although the captions file is not as a CSV, so we'll probably need to process that. Otherwise, the images are okay. They're relatively um, processed. There's not much processing needed on each individual image. However, we will need to do some amount of pre-processing because we are using a pre-built image classification and object detection model. It's a fairly famous model known as VGG19. We're using their pre-process input, but we're not using that to create our model. Our model simply takes the parameters, or in other words, the features generated by the model, and uses that to predict the caption of the image. We have used different libraries in this project. We have used TDQM to give us a progress bar where we needed. Um, the TensorFlow is used to create and load the models. I have pre-trained the model, so I'll probably be loading that instead of training our own since it takes a lot of time. Matplotlib is used to generate plots. Seaborn is used to do the same, but with better quality. We're using Matplotlib specifically to show images in this project, not much else for that. Um, these are just defining the variables, the paths to the images. Actually, the working directory, which is the input, or my mistake, the output. Input is the base directory. As I was saying, we're using VG19 to generate the features. We're not using it in our model. It's not a part of our model. We're just generating the features. We're doing that by cutting off the last two layers of VGG19. Uh, if you look closely at the given architecture, VGG19 performs a lot of steps. It does convolutions, then max pooling, which lowers the size of the image, then convolutions again, which multiplies the given image with a kernel to slightly decrease either the size of the image or bring out some features. The weights are in a CNN the values of the multiplying kernel matrix. The size is reduced every time we max spool, which is simply taking out the maximum from any given batch size. And stride is simply the jump we make. We'll see the specifics later. However, you can see that we have reduced the size and eventually we end up with a relatively small output. This is then fed into a fully connected feed-forward network, which uses relay activation, and then softmax, which gives us the output. So we have cut off up to here these last two layers, which leaves us with a model that starts with the input. The input, by the way, needs to be 224 by 224 in RGB. It does all the convolutions, then max pooling, and then convolutions again, then max pooling, convolutions, max pooling. It goes on, and at the end, it flattens the output, feeds it into the two dense networks, two layers of dense networks, the output after which is 4096. This is the output. This is the actual features that we're going to be using. These are the main thing that we are using to train our model. Here, we are generating the features. We are going through the directory. TDQM is simply to provide us with a progress bar. You can simply do, you could remove that if you wanted. We're picking up each image, converting it to a NumPy array, reshaping it, right, into three, a 1 by 3 matrix, right? So each value, each array has the 3 individual pixels, basically. We'll be processing the image, then we are using the model to predict, which means it'll simply generate the features array. We're using the name of the images. The images have specifically coded names, so we're excluding the JPG part. We are saving in the dictionary at the key of the image ID, which is the starting part of the name of the image, the features that we want to save, right? And if you want to load these features later, we are using Pickle to save that, right? And then we could simply reload those. Once we have done that, we have features. Now we need the captions, which are provided here. You can see the format that they're provided in. It has the name of the image, then the actual caption that it needs to give to the image, right? So we read the file into the document, right? And then we go through the captions. We clean out the tokens. We get the image ID, we get the caption, and then we get, in case the tokens or the caption, since we're splitting the tokens based on commas, we would need to join the rest of the token because it might have commas within itself. So the first word would obviously be the name of the image, right? And the second word would be the rest of the words would be the caption. So it might be possible that there might be a comma here. So we are not, we have to join the captions, right? This might possibly be an array, so we might have to join. And if we can't find the image ID, right, then we add it as an empty array and we append the caption. So it may be possible that one image might have multiple captions. So we are checking that case as well. It is hard to find on a first go, but there are multiple captions for the same image, right? So the mapping is as follows. So we process the image captions. I should probably start speeding up. So for each image, there are multiple tokens in the mapping. That's how we have created it here, right? And Then we pre-process the mappings using the function that we created, right? And here is the pre-processed image text. You can see that we have added a part that I skipped over. We have added a start sequence and end sequence to the caption text that we already had. That would make it easier for the model to learn the pattern of the image, or it would make it easier for us to determine where the actual caption starts and ends. So after pre-processing, we have removed the starting few words because almost all of them have that sort of words which are not really useful. We have removed those. We have changed the inconsistent capitalization. There's a few examples, not specifically these ones. We've done the basic pre-processing for that. Then you can see we have around about 40,000 captions, which is a lot. The first 10 captions are such, but we have only 8,000 images, which means there's a lot of captions per image. So we tokenize based on all of our captions. Tokenization basically means converting the words into a vector space of numbers. So the models work with numbers, not specifically the ASCII sort of numbers of characters that we're used to. They work better with tokenizers that create more semantic number spaces. Tokenization is basically done using sequence of characters or words. Tokenization on each dataset would be separate, but nonetheless, I should skip once again that using all of this text and all of the captions, we have generated tokens, right? We have fitted on our captions. And you can see the vocab size, which I have probably printed here. There are 8,485 unique words. And you can see the caption length is sort of normally distributed. The maximum you could find is 35 length, right? You can check this through the verification if you want to do. You see you can have at most 35 length of caption. That's just how our dataset works. You split the dataset 80-20. So 20% of the data goes into the test, which is here. And the rest of the 80% goes here. The random state simply randomizes the data before splitting it instead of using the default ordering. We have created a function for data generation. All this does is get all of the specific inputs that we have. This will be used later, so I'll explain it in detail later. But for now, you can see that we have two inputs and a while, right? So we're using two specific separate inputs and giving the prediction. The data generation will be used later, so I'll show that later. However, as you can see, we have imported all of the needed TensorFlow libraries. We will be using LSTM, dense layers, embedding layers, dropout layers, and bidirectional LSTM layers. So this is the architecture of our model. Here I have plotted it out. It takes the features from here, right? And it takes the rest of the input from here. The input that we give from here, you can see, I'll show it to you later. This goes into the embeddings, then the dropout, then the LSTM, and then we do a batch normalization. And the other side, we have a probability of losing it, which is the input, which is a dropout. And then we have the dense layer, then batch normalization, and then we add the two together. The added outputs go into a dense layer, then we batch normalize, and then we go back into a dense layer. The output of this is the tokenized size. You can see the unique word count that we had. So it will generate a combination of tokens. We'll use that combination to generate sentences. So here's the code to train the model. I tried to train the model on 100 epochs. This causes a problem. I intentionally did that to show you said problem. Epoch simply means the number of times your data or your model sees your data and learns from it, and we adjust the weight. So 100 epochs means that it sees the data 100 times and adjusts its weight. Batch size simply means how many times steps is specifically how many specific times we change the weights, simply. I had implemented checks to stop early in case we don't get any improvement. I'll show you what validation loss is later. However, the model checkpoint is just to save the model in case there is some problem. We'll be saving it into this variable and into this file. We go through each epoch. We get the data through the generator. The generator, by the way, yields an output every time we call it. Yielding simply means that every time the function is called, this loop goes through one iteration, and the second time the function is called, it goes through its next iteration. So it doesn't completely clear all its iteration in one function call. Every single time you call, here we stop, right? And then when it's called again, this runs, and then we go on to the top and run the rest of the function, right? So the data generator gives the input into the model on each epoch, right? And then we have a validation generator. What this does is give us the inputs from the testing dataset. Why are we showing the input, the test dataset to the model? Well, we're giving this as validation data, which basically means the model does not update its weight based on a testing dataset. What it actually does is it compares the current performance on uh, the testing dataset on each epoch, right? So I'm not going to train the model once again because it takes a long time. As you can see, I had stored the values of the loss and validation from the previous run that I did. And as you can see, the model stopped working at around, I think, 71st epoch. That was because the provided free RAM ran out. Nevertheless, you can see if we separate out each element that the model learns and it keeps on learning from the training data set. But there comes a point where it actually stops improving in terms of the testing data set. This happens because we are showing the model, the data set, way too many times, right? This causes the model to overfit and hence perform not that well on the testing data set. Therefore, I had saved the model on each epoch. I saved it specifically on the fourth epoch because, as you can see, around the fourth, it performs the best. And after that, I've stored it on every 10th iteration, on every 10th epoch to see how the model progresses. Uh, I have not, I will not be training the model again. You can train it if you want. Here are the functions to convert the integers or the input array given to us into the words, the textual output that we want. We use the tokenized as word items that we have created earlier, right? And we return each word. We give the index of the output array, right? And each index is a word. So we take set word from the tokenizer and return it. Simply, this function is doing that. I'm loading the 70th um, epoch model. The sample function simply adjusts parameters based on temperature. Temperature, you can consider the creativity of the model in simpler terms. This function is simply to call the model with the image loaded and try to predict. This is specifically me opening this function simply takes an integer and loads the image from the testing dataset, and then we test or predict as we had created the earlier function. Then we predict the output. So here you can see on the 97th image, a person is standing on a mountain with some sort of ocean behind it, and it has predicted that the man is climbing the desert, which is slightly wrong, overlooking the ocean, which is close enough, I guess. It's not performing that well, but it's close enough. Let's test another image. Four people are riding horses on the beach. This is wrong, but you can see how it came to the output. It came to the output since it thought there are four dogs, and they're looking quite similar to riding horses. So it tried to guess that. If you run it again, it might make another guess, which may be correct or maybe wrong further. It's once again guessing four people, this time purchasing tickets. It won't give that conclusive of a value since the model is that simple. And it's quite simple, so it would at least give us answers close to what we want. You can go to, say, fourth. See, man in yellow shirt, incorrect. If it tested it might give better. Three women sitting in a grassy lawn. There's a grassy lawn. There's a woman, a tiny woman, but around three women. Try again. And playing two dogs, incorrect again. But you can see that it's basing it off of some sort of semantic mean right from the image. That's just another image. Hopefully, it looks this one. It'll give close enough answers. So, for instance, it found a blue hair, and it found a person in a shirt, so it thought it was a person with a blue shirt, right? It is making logics out of things, but they aren't that well thought out. This is close enough. Although this image is an abnormality, which is hard to classify for a model. This sort of image would be a lot easier. There are men wearing shirts. It's classifying close to what we want, but not exactly how we want it to. Nevertheless, the model performs this way. We can test the performance of the model by checking its below scores. Uh, I have ran the model on each test input and predicted the outputs, right? And then we compare the sentences of the actual caption and the one we have predicted with the following below weights. Uh, then we append the score that it gives into the array. Later, we are using set scores to draw this graph. Now, this shows that it gives the specific frequency on the following below scores. As you can see, we have gone through each key and we have tested what it does. And then we have gotten the actual captions, right? And then we have split the predicted text since it would be a text. And then we have compared the two to then compare the sentences. The actual comparison, the below comparison is provided to us by NLTK, the below score function, as well as we can later use the corpus blue or the sentence blue. Sentence blue compares to sentences. Corpus blue compares to sets of arrays of sentences. Um, so here you can see the distribution of the below scores, and this was the actual product that we have made. Thank you for listening.